Okay, this is a nice paper with some prominent authors who are known for their high resolution modeling, which includes urban heat island effects and other impacts of urbanization on regional climate and extreme weather. It's a review article that is relatively long, over 40 pages, of course, with lots of incredible references. Looks at what we know already and what the uncertainties are and what future research directions are based on what we know and what we need to know. And it's a fairly straightforward paper, but I'm going to be supremely brief. Let's just read the abstract and look at a few figures and make a few points. Urban environments lie at the confluence of social, cultural, and economic activities. They are a magnet for employment-seeking migrant labor, for example, and have unique biophysical characteristics due to continued infrastructure development that generally replaces natural landscapes with built-up structures. So you change the runoff, evaporative cooling, thermal radiation loss during the day and night, and so on. The vast majority of studies on urban perturbation of local weather and climate have been centered on the urban heat island effect, referring to the higher temperatures in cities compared to their natural surroundings. Besides the UHI or urban heat island effect and heat waves, urbanization also impacts atmospheric moisture, wind, boundary layer structure, cloud formation, dispersion of air pollutants, precipitation, and storms. In this review article, we first introduced the data sets and methods used in studying urban areas and their impacts through both observation and modeling, and then summarize the scientific insights on the impacts of urbanization on various aspects of regional climate and extreme weather based on more than 500 studies, so it's an extensive meta-analysis. 500 studies. We also highlight the major research gaps and challenges in our understanding of the impacts of urbanization and provide our perspective on our perspective and recommendations for future research priorities and directions. Meta-analysis always have to synthesize what we understand, what we need to understand, and how to get there, right? The article stress some points. As urban areas expand and populations grow, density of population within the cities are growing, and urbanization itself will continue to grow. We urgently need to better understand cities and their interactions with weather and climate. Cities contribute disproportionately to climate change, as well as being disproportionately affected by climate change. And density of population being high, obviously exposure to hazards tends to be very high. Urbanization can impact heat waves, atmospheric moisture, clouds, wind patterns, air pollution, boundary layer, precipitation, and storms, as we said. Research gaps due to complexity of urban areas and deficiencies in current methods are identified, and future priorities are highlighted. We start off with a schematic here, which is showing the inputs into an urban center and the outputs. Urban centers have to get power, fuels, and raw material, water, and food typically from outside. Very little energy can be produced inside, even though maybe solar panels and maybe windmills are increasing these days, and hopefully will continue to produce more and more renewable energy from the cities somehow. So clean air may be flowing in and polluted air may be going out, with modified atmosphere, emissions of aerosols, pollutants, and water vapor happening inside. Once you pave the land, any water that falls is going to be runoff, or it's going to just evaporate. And waste heat, of course, is generated from all the buildings and other activities. Storage and internal flows, depending on how well the adaptation measures are put in place. You could have rain gardens, permeable pavers, and other adaptation measures that can absorb the water that is coming in instead of just running it off into neighboring coastal waters or other water bodies, and so on. And you have coming out solid waste, which is produced massively by these, and they cannot handle it inside, though typically they pump it out to some facility. And of course, degraded water is flowing out for wastewater treatment. And manufactured goods, depending on what activities go on, often they tend to be producing electronics or other goods that are often centers of employment as well. Urban heat island effect, this is the surface heat, sorry, just the schematic which typically you see in lots of places. Late afternoon temperature in degrees C, so you have a rural land use type coming into suburban residential areas, which are typically around every city as suburban peri-urban interfaces, and you have various types within commercial, city, residential area and park. So you can imagine that air is coming in or temperatures being measured. It jumps up already in the suburban residential areas, but once you get into city centers, it can really spike because of the urban heat island and then drop off. Maybe the park is providing some much needed cooling, but then you jump up again with the suburban residential area before you tail off to the larger temperature range in the climatological background. We'll see summer and winter temperatures in a while, in a minute, but this is a typical schematic. Of course, each one can be different. For example, in India, sometimes abandoned farmland in rural areas can actually warm much faster than the cities nearby, and there are many examples like this. Overview diagram of ground-based versus satellite observations of urban temperatures, their advantages and their disadvantages. Ground-based sensors can provide all sky estimates. They are not affected by clouds and so on. They are cheaper to maintain and easier to calibrate and fix, and measurement can be what people actually feel when they are living on the ground, because they are the temperatures are being measured very close to where they live. The disadvantage, of course, it can be locational bias because you have only few instruments across the city and rarely available for urban areas. And measurements valid in the sense, if you look at the land use type, they may be situated near the airport, for example, and so on. Measurements valid for local footprint, not a graded product. Sensor accuracy differences drift over time, standard things. But if you have satellite observations, they of course provide you a global scale observations, and you can see the contrast of the urban heat island effect, and identical sensors that flying around giving global maps, spatially continuous estimates, logistical simplicity and widespread data availability. Kind of a very simplified list of advantages and disadvantages. Clouds can be a problem, so you tend to get mostly clear sky estimates. View angle differences, satellite configuration and orbit can make a difference. Atmospheric interferences and empirical assumptions involved in converting radiances into temperatures. Not equivalent to human perception of the environment. So people living on the ground will see what's measured mostly by ground-based sensors, whereas these are derived quantities from radiances, which can be different. That's why we have things like surface heat island and atmospheric heat island. So if you look at the models that are typically around, you have urban representation models with a slab model, which has basically atmosphere that is represented above the ground, and here you have surface temperature, that's ground temperature. You have land atmosphere energy exchange, which then determines the atmospheric temperature, which is obviously also affected by large scale circulation and local climatology, etc. Single layer urban canopy model, Slocum, obviously has multiple levels being shown here within the boundary layer. You can think of it that way. So you have ground temperatures, energy exchange happening vertical and horizontal. So you have different levels of temperatures and energies being measured, and you have again the free atmospheric temperature. Of course, it depends on how high the urban canopy itself is. Okay, multi-layer urban canopy models, MLUCM, I don't know if that's the way they are pronounced, but anyway, obviously has more sophisticated energy balance calculations to determine temperatures than the single layer or the slab model. And if you have building resolving model, then you begin to include more energy exchange directions. So you have here one oblique line which is not here, and you have of course vertical exchanges from the ground and from the various levels of the atmosphere before it reaches into the free atmosphere. Okay, so it's very brief, but you can go and read the paper. It's very useful in terms of the details of how the models are different and what they are good at and bad at resolving. If you want to do urban meteorology, obviously you will use a very realistic building resolving multi-layer urban canopy model, and there are also experimental sites. I've been to one in China, in Guangzhou, for example, where a little area of, let's say, 50 square meters is set up with actual cement structures that look like buildings, and they have airflow and impacts being measured, and people who do energy calculations, optimizations, etc., also do those kind of high resolution, direct numerical simulations, large eddy simulations, and so on, to capture the details of airflow in the urban canopy. Okay, so this is an example of how distribution of daytime, did I jump any figure? No. Distribution of daytime surface urban heat island SUHI for summer and winter for over 10,000 urban clusters across the globe and across different Köppen-Geiger climate zones, which are basically these here: tropical, arid, temperate, boreal, and polar. This is based on some data set from Yale, but basically you look at daytime SUHI urban heat island temperatures going from the cooler times before the peak into the let's say evening hours, so anomalies. Urban heat island impact is basically anomaly from some baseline, because that's how much warmer you are compared to the surroundings that we looked at before in terms of urban to suburban and so on. So density of the urban structures matter here in terms of the exact peak. During summer and winter they will be different, and you can see in the winter it's much warmer here in terms of the scales are different, so you have to be careful. This is going from 1 to 3 degrees, whereas this is only 0 to 3 degrees, whereas this is only going from 0 to 1.5 degrees, so it's misleading a little bit. I have to be careful. So obviously depends on the background climatology. Summer, so tropical region is here, basically coming into daytime SUHI. It's cooler, then warms up to about 1 degree and then tails off with tails over 3 degrees C. That's the tropical one, but you can see temperate regions and boreal regions can have higher densities of cities. So this is basically a meta-analysis, so they are just taking the data as is available. It's not normalized for density in that sense. So arid regions, obviously maybe fewer cities, but it's peaking around 0 and then tailing off. What else? Polar regions are showing much higher density, and they are let me just clarify something here. Let me stop this for a second. Yeah, so building density, the density is basically dependent on the street width, building height, and roof sizes. So it's essentially, you can think of it as how much area is emitting thermal radiation and how it can trap them. So density matters in that sense, obviously, but you can go and read the details. So for whatever reason, polar urban areas have large spikes in density. Maybe they are richer countries like Norway and the Sweden. Those, they are not polar climates, so they are high latitude cold countries. They do have a strong summer, but you can see in the summer also they have a similar spikes in densities, but now you have daytime temperature that is very different in terms of the distribution and the magnitude, but you get the idea. Okay, I don't want to spend too much time on the detail because it's a meta-analysis and it's combining many different urban canopies in trying to synthesize the relation between density as defined by ratio of width and height and the valley depth, etc., with summer and winter. So take what you want to out of it, or follow up with details if you are interested in really exactly what's happening. And here, typical overall form of urban boundary layers at the mesoscale. This becomes important as to how the energy is carried away, how it's ventilated, how it affects the atmosphere, precipitation, clouds, water vapor, etc. Right? No ambient wind, so rural boundary layer is here, and air is flowing in, and it's having these mesoscale circulations because of the heating, and it basically warms and pushes up the boundary layer, so the boundary layer grows in height, and then it sets up these circulations, mesoscale circulations, and then you can create large scale convergence because of the heating. Obviously, if you heat, warm air rises, then you have to converge air, and that can also pump up the boundary layer, but that rising air can cool and evaporate and create clouds, not necessarily rain clouds, but kind of a shallow cumulus as shown here. But if you have urban internal boundary layer and downwind plume in moderate regional airflow, so this is as if the city is just sitting there and then heating and creating its own circulation, and there is no background wind. Here you have some ambient wind, so there is the rural boundary layer again, and now you are blowing air from one direction, as we said before, and polluted air, humid air, aerosols, greenhouse gases, etc., are flowing out, but you are again having the impact of the heating and water vapor creating boundary layer clouds. These are typically just at the top of the boundary layer, so they are shallow cumulus type clouds, not rain bearing clouds. To look at some impacts quickly, these are airfield specific relationships between changes in temperature, urban cover at different temperatures, local standard times, stratus cloud base height, and fog frequency. And each dot here represents one of 24 coastal Southern California airfields, and dot colors indicate the sub-region. Essentially, only one region, western coast of the US over California, is looked at in airfield experiments in terms of urban fraction versus impacts on trends in minimum temperatures. So that's degree centigrade per decade. You can see they are statistically significant, and obviously as urban fraction increases, minimum temperature tends to increase, so correlation is significant at 0.78, which is very high, but the maximum temperature doesn't show such a strong correlation. If anything, shows a small negative correlation, but it's not that statistically significant. If you look at the stratus cloud base height, which is thin clouds which are warming clouds because they allow sunlight to come in, or they cool. Yeah, typically stratus clouds tend to warm. So you can see again there is the increase in height in meters per decade as the urban fraction increases. So significant correlation, just under 0.7 as well. And there is a significant scatter here compared to the scatter here as well. And this is for stratus cloud base for different times. Okay. Fog frequency is shown here. Fog frequency drops as urban fraction grows, because you don't, fog is basically cloud that is touching the ground, and it typically needs water vapor, which typically comes from soil moisture or groundwater, and if you urbanize, you are going to reduce that, right? So this is delta fog per decade in terms of temperature uh, or urban heat island effect. So as temperature increases, obviously you're going to reduce the frequency of fog. So just confirms that pretty much everything is affected by the urban canopy or urban land use type. See, this is conceptual understanding of urban rain effect. So you have different discussions going on. Urban heat, thermal boundary layer perturbation, and urban heat island circulation that we mentioned already mostly enhances precipitation downwind of the city. Okay, somewhat like this, let's say. Okay, there are many details. These are kind of phenologies of circulations they found from the meta-analysis. Urban surface roughness can affect the wind speed, reducing it and creating convergence. Impact on rainfall is unclear. Urban heat island circulation and urban morphology itself can affect the convective systems by splitting them, and this was looked at over Minnesota by one of my students, Manisha Ganeshan, and clearly showed such an effect. And that can create downwind convergence, and this may increase or decrease precipitation depending on the specifics. Urban aerosol loading can cause radiative cooling, so increased cloud condensation nuclei can occur because aerosols can act as CCNs or cloud condensation nuclei. This can suppress or enhance rainfall depending on various other factors. In other words, there is no typical one single process that relates urban impacts to precipitation impacts, urbanization impacts to precipitation changes. Depends on various details, but clearly they affect rainfall and storms. Okay. Jumping straight ahead to summary and future directions. Again, I'm hardly going to read any of the long text there. Summary of current understanding. Below, we provide a summary of our current understanding of different aspects of the impact of urbanization on regional climate and extreme weather based on observations and modeling. Very nice details there, synthesis of all those papers that you can read. They look at impact on temperature and heat waves, what we know and what models say. Impact on planetary boundary layer and clouds and air pollution, precipitation and storms. So they provide nice details in each one of them. In the meantime, schematic picture of urban impacts on weather and climate can be looked at this way. At the building level, you have solar panels, reflective material, and heat exchange in these directions, building heating and cooling. So here is where you are trying to be effective in managing urban heat island effects as well as climate adaptation. You want to reduce heating and cooling requirements by using natural light and natural circulation and so on. Maybe want to generate some renewable energy with solar panels and use reflective materials to alter the albedo and reduce heating. Of course, in winter you need that heat. So there are now materials or paints with have specific abilities to change their absorption and reflection based on seasons, or we can change them. Various fancy things are being tried. Of course, there is the background wind, boundary layer rises over the city center. Downstream, you can imagine clouds and rain, as we said. So heat island effect from rural to pollution sources in the suburban or city centers, and some efforts to green the cities and create cooling. So heat island effect drops, but you can have inversions and pollution domes trapping the pollution, which is not good. And then you can create thermal convection because of all the rapid warming of the buildings, and this is where a lot of the urban heat island comes about. Of course, raising the temperatures, and then can drop off. So just kind of what you need to model. So a schematic figure of an integrated urban system model as they see it is to have urban carbon emissions tracked, air and water pollution, water, food and energy sustainability included, adaptation policies, urban farms. This is becoming more and more common to create spaces where you can have vertical farming and horizontal farming and so on, to give people social activities, social bonding, as well as green spaces, and maybe generate enough vegetables within the city's boundaries. Extreme weather, human thermal stress, urban ecosystems, such a thing does exist. Urban water and energy cycles, man-made hazards, sea level rise and floods for inundation for coastal cities, and floods are very common for urban centers because of the paved areas and no water to run away, and impacts on extremes. So urban weather and regional climate interactions. So very schematic, but you can see the prop in the back with this incredibly packed population. Maybe that's a picture from a marathon or something. When you have marathons in New York City or Boston, wherever, you have, you know, literally tens of thousands of people starting at the start line, and then quickly it gets segregated into professional fast runners and the slow runners and so on and so forth. But nonetheless, it's not uncommon to have very high population densities, but the idea is that eventually you want to have this entire thing modeled like an regional earth system approach, where you are also including greenhouse gases and carbon and urban meteorology and aerosol impacts and adaptation impacts, as well as other human dimensions and so on. Okay, it's a nice paper, long paper. As I said, I'm going to be shamelessly brief, but hopefully it still gives you a sense. And if you are an expert, you want to read the paper and understand more. If you are not, hopefully this gives you enough of an exposure to what urban heat island effect and urbanization impacts on regional climate and extreme weather in general are. Okay, see you in the next topic.